Today's lecture is on optimization, part 1. So the idea behind optimization is find, in some sense, the most optimal value. When we're talking about functions, this typically means finding either the minimum or the maximum values. And they could be local, which means, let's just look at an example like this. This actually has two local maximums and one local minimum. So here's a local max, here's a local max, and then here's the local min. So you have max, max, and then you have min here. And then for global, so this is a little bit different. Global is actually, a global maximum is the very highest point, whereas a global minimum is the very lowest point. So on this graph, let's do this in blue. All right, so there is one global maximum, so here's a global maximum, but there's no global minimum. There is a local minimum, but no global min. And that's because this function continues to go down. Actually, it doesn't matter which side, but on one side it goes down, and this happens to go down on both sides. So hopefully you have the idea. So what we want to do is find a way, how can we find local minimums and local maximums? And then how can we find global minimums and global maximums? And there's two ways to find local minimums and maximums. One we've already done. It's called the first derivative test. And it's really just step 1 and step 2. So if you remember in step 1, we take the derivative and set it equal to 0 or find where it's undefined. So we find these critical points. And once we find the critical points, we can plot them on a sign diagram for f prime. So here's f prime. We plot the critical points. So suppose there's two critical points. And then we can figure if f prime is, let's say, positive here, negative here, and positive here. And then for f, we can conclude above it. So let's do this in red. If it's positive, what's going to happen to f? Well, it's going to go up, it's going to go down, and it's going to go up. And so maybe this is a max. As long as it's not an inflection point, right? That's a maximum then. And we can see there's going to be a minimum there. So that's the first derivative test. Now the second derivative test, which we're going to do today, involves the same step 1 and the second derivative. Now remember, the second derivative tells us what about the function? Well, the first derivative, right, f prime, tells us whether it's increasing or decreasing. The second derivative, the sign of it, tells us whether we're concave up, so CU, or we're concave down, CD. Let's make that a little bit better. So concave up, CU, or concave down. So the second derivative is positive, it's concave up. Second derivative negative, it's frowning, it's concave down. And it's obvious, if it's concave up at a point, then what do you have, a min or a max? Hopefully you say concave up must imply you have a min here. And if it's concave down, you're going to have a max. So let's take a look at how we would do this. All right, so here's our first example using the second derivative test. So we have f of x equal to x cubed minus 9x squared minus 48x plus 52. And we want to find any local maximums and minimums if they exist. Now it could have just a local minimum, looks something like that. It could just have a local maximum, looks something like that. It could have neither. It could be a line, which has neither a local min or a local max. So let's see what happens here. So the idea is first do step 1. And so on step 1, this is find the critical points of f. And so that's when f prime of x is equal to 0 or undefined. And so let's do this. So let's find f prime of x. So f prime of x is equal to, this is nice and easy, the 3 comes down, I get 3x squared minus an 18x minus 48 plus 0. And then I'm going to set this thing, it's defined everywhere. All right, so defined everywhere. That's because it's a polynomial and there's no denominator, there's no square roots, and there are no ln's. And now I'll set it equal to 0, so 3x squared minus 18x minus 48 equal to 0. And hopefully I can factor out this 3, otherwise it's going to be a pain. So it looks like I can. So this is going to be an x squared minus a 6x, and then minus, let's see, 48, is that 16? Yeah, 16. Equal to 0. And then maybe, hopefully, I can factor on the inside. So it's going to be x plus or minus something, x plus or minus something equal to 0. And the something, when I see 16, I think first 4 and 4. But there's no way to add or subtract 4 and 4 and get negative 6. So then I think 8 and 2, and I could do minus 8 and plus 2. That 8, let's make it look a little bit better. All right, so minus 8 and plus 2. And so I know 3 is not equal to 0, right? So I know x minus 8 is equal to 0, or I have x plus 2 equal to 0. And so I get 2 critical points, x equal to 8 and x equal to negative 2. So those are my 2 critical points. And now I'm just trying to figure out if it has a local minimum or local max. Now I could do step 2, which would be a sign diagram, and then I can figure out, if it's decreasing, increasing, it'll be a min. If it's increasing, decreasing, then it'll be a max. But I want to use a second derivative test, which means use the second derivative to test whether these are local minimums or maximums. So second derivative. So let's do the second derivative here. So the second derivative. And a lot of times I'll just write second derivative test, even though the test is kind of the whole piece. I just kind of write it anyways. Because I just do the second derivative, so I need to find f double prime. So let's keep f prime on the page. So f double prime of x is equal to, and I come back up here, and I'm going to take this derivative. The 2 comes down, and I get 6x minus 18. And then I'm going to test these points. So let's just take a look at each of these points I found. So let's look at f double prime of 8. And so that's equal to 6 times 8 minus 18, which is 48 minus 18, which equals 30. Now 30 is bigger than 0, so that implies that this is concave up or concave down. Right, so bigger than 0 means this has to be concave up. And if it's concave up, that implies f of 8, which is equal to, so now I'm going to go back up here, and I'm going to plug in 8 all the way up here. I'm going to go back up here, and let me highlight this for you. I'm going to plug in 8 into here. And so I'm going to do that on my calculator so I can save some time and some work. So on my calculator, what I would do is I would just plug in 8 for x. So I have 8 raised to the 3 minus 8 raised to the 2 minus a 48 times 8, and then finally plus a 52, and hit enter, and I get out 116. And so I plug that into, and there's a mistake here, right? I forgot the 9. That's why I was slowing down, because I'm looking at my notes, and it's not supposed to be 116. So second enter, this is supposed to be a 9 in front of the 8 squared. So over here, there should be a 9. So second insert, there should be 9 times. Now you get the right answer, negative 396. So down here, all right, negative 396. And what is that, a local min or local max? Well, because it's down here, this is a local min. And then we'll do the other point. So let's do f double prime of negative 2. So f double prime of negative 2, which would be 6 times negative 2 minus 18, which is equal to, this would be minus 12 minus 18, which would be equal to negative 30. And since that's negative, that implies the function f is concave down. And so that implies that f of -2, so again, go back up here and plug in now -2 for x, and you'll wind up getting out 104. And that's my answer. So 104 is a local max. Now, if I have time, I could actually check this problem probably on my calculator. So if I had time, I can check my work here by actually graphing this thing on my graphing calculator. And you can't solve the problem like this, but you can always check your work with it. So x raised to the 3 minus 9, x raised to the 2 minus a 48x. And so if there's time on the exam, I usually come back and I would do this. And now my window, the way you make your window is this is your critical points for 8 and -2. So I'd probably do -3 and 9. Just go a little bit to the left and a little bit to the right, and then zoom fit it. And you should get a pretty good picture. And hopefully it's good enough that you can see where the local minimum, local maximums do occur. So, you can trace this and do -2 and see, yeah, you get out 104 and it's up there, it's flashing, but you can't see it. And then if you trace and do 8, oops, I hit the wrong button. All right, so let me go back, -3 over to 9, zoom fit it. So let's do this one more time. So I'm going to trace in 8 once it's graphs here. So trace 8 and then enter, and I do get out -396. And it should be a local min down here. So I can check my work by doing that. But you can't do the problem like this. Right? You have to run through the analysis. The idea is, can you figure out how to do this without your calculator? Of course, your calculator can do a lot of things, but our goal is to understand, why it works. So why do we use the derivative? A derivative tells me increasing and decreasing. Why do we set it equal to 0? Well, think about it. All right, if you have a local min or a local max, so here's, say, a local max and here's a local min, what's the rate of change at these points? Well, the rate of change, or the slope of the tangent line, is 0. So take the derivative and find out when it's 0, so 8 or -2, and these are possible local mins or local maxes. I say possible because it could be that we're in this situation. If you take the derivative of this function, it's certainly going to have a 0 for the derivative here because the rate of change is 0, but it's neither a local min or a local max. So it might be a local min, it might be a local max, it might not. You have to check the concavity, or you can check the concavity by using the second derivative test. Now, just sort of a bonus question, what would the derivative of the function, if you plug this point, let's say, into the derivative, what would it be? And hopefully you say it's 0 because it's actually an inflection point because it's concave down, concave up. All right, let's move on. So the next thing we want to take a look at, oops. So the next thing down here, we want to figure out how can we find now global maximums and global minimums. So not just local minimums or maximums, but the basically absolute highest point, right, the very highest point, or the absolute lowest, the very lowest point. And the way we do this is we actually use this extreme value theorem because we're going to deal with most things just on a closed interval. It is possible, like we saw at the beginning of this lecture, for a function not to have a global minimum. It's also possible for a function like this one not to have a global maximum. It's always possible for them to have neither a global minimum or a global maximum. So this one just goes down all the way and goes up all the way. And so we want to have a condition where we know these global maximums and minimums occur. And understand the application behind this. So the idea, in an applied problem, you're often looking for that best value. And that typically is the highest or lowest value. So like suppose you're trying to price some sort of product. Theoretically, there should be this optimal price where you get the most sort of return after selling your product, your most profit back. So consider like a movie ticket. Right? If you charge too much for a movie ticket, suppose you start charging $20 for a movie ticket, what's going to happen? Well, hopefully you say no one's really going to go, and so you're not going to make that much money. Now, if you don't charge enough, suppose you charge $2, now a lot of people are going to go, but again, you're not going to make a lot of money off of that because you'll fill the house, but you still won't make that much money because it's just $2 a seat. So somewhere in between $2 and $20, let's say, there is this optimal movie ticket price. At that price will you get the most profit back. And now that price might be $6 or $7 or $8, but our goal typically is to find these prices, and they change all the time. So for us, we're not going to do something as complicated. What we're going to do is we're going to have a function on a closed interval. So the idea is we'll have some function f of x on some closed interval, so from like a to b, including the endpoints. And we know by this extreme value theorem, what it says is if this function is continuous on this closed interval from a and b, then it will obtain its global maximum, global minimum on that interval. So you won't have one of these situations basically going on. It won't, go off to infinity or off to negative infinity within a and b, inside that interval. So let's just take and the way we're going to do this is actually quite simple. You're just going to do step 1, all right, because you could have a local min or local max could be your global minimum or global maximum, and then we're going to do a table. And in a table, we're going to make sure we plot the endpoints, because what's going to happen here, so think about this. If you're on a and b, what could possibly happen? Well, you could have a function that looks kind of like this. And now where would the global minimum occur? Well, hopefully you say the global minimum is this height right here. And the global maximum now occurs at one of the endpoints. So what we're going to do is we're going to make a table for the second part where we plug in the endpoints along with the critical points. And over here, then we can figure out, like in this case, it'd be this height was the global max, whatever number that might be. And then the global min wouldn't occur at A, it'd occur at the critical point. So this would be then the global min, whatever number that turns out to be. All right, so let's take a look at 2 examples. The first one's a nice, easy polynomial. So it says example 2, example of using the extreme value theorem. We have this function, and let's just write this down. So example 2. Let's switch back to black. We have part A. F of x is equal to 3x to the 4th minus 16x cubed plus 18x squared. And we're on this interval from negative 1 to 2. So all we care about are the numbers between negative 1 and 2 and including negative 1 and 2. And these are inputs, so they're x values. And so the way we're going to find these global maximums and global minimums, and I know they exist by this extreme value theorem, I just got to figure out what they are. We'll do step 1, and again, I'll just keep copying this down, find the critical points of f. So that's when f prime of x is equal to 0 or undefined. And so down here, I'm going to take the derivative, f prime of x. And this one's nice and easy because it's a nice polynomial. And this is 12x cubed minus, and then times 3, I think this is what, 48x squared plus 36. The 2 comes down, 36x. And now this thing is defined everywhere. And because it's defined everywhere, I don't need to worry about it being undefined. So defined everywhere. And now I'm just going to set it equal to 0. So I have 12x cubed minus 48x squared plus 36x. And when I set this equal to 0, I realize I can factor out a 12x. And then I have x squared here minus a 4x, and then plus 3. And that's supposed to be equal to 0. And I can continue on. So that's 12x. I can factor this quadratic, so it's going to be x plus or minus something times x plus or minus something equal to 0. And now 3, there's only one way to get 3 by multiplying 2 numbers, and that's 1 and 3. And the way to get negative 4 is to take negative 1 and add negative 3. So that's negative 4. So that should work. And I'm actually going to get 3 points here. I have x could be 0, so 12x could be 0, so x is 0. Or this could be 0 right here, which means x is equal to 1. Or this could be 0 right there, which means x is equal to 3. So you have 3 things. 12x could be 0, so x is 0. X minus 1 could be 0, so x is 1. Or I could have x minus 3 equal to 0, so x is equal to 3. So you find 3 critical points. And then the trick is this. if I want to find the global max and global min, I'm not talking about local. All I want to find is the very highest and the very lowest point. So all you really need to do is a table. And in this table, what you're going to have to plot is you're going to have to plot the endpoints. So you just have x, f of x. And so the endpoint, where do the endpoints start? So let's change colors here. Let's use red. So the endpoints start at -1 and the end at +2. So I'm going to come down here. I'm going to put -1, and then I'm going to end at +2. And those are the only points I care. The only thing I care about are points between these 2 points. So starting with -1 and going to 2. So when I look at this, I look at 0 and I say, oh yeah, 0 is right here. That's great. And then comes 1. It's right here. But 3 is after 2. So I don't care about that 3 because it's outside of my interval of concern, really. All I care about are these 4 points. So I want to figure out what f of -1 is, f of 0, f of 1, and f of 2. And so now I'm going to go take out my calculator. I'm going to come up here, and I'm going to plug in these numbers into my calculator. So let's just zoom out just a little bit so we can kind of watch this occur. So I'm going to plug in -1 first, and make sure you understand what I'm going to plug this into, because I'm not going to plug it into the derivative. I'm actually going to plug it into the original function f, because that's where the actual heights are. And so I have 3 times left parenthesis -1 raised to the 4, and I could probably do this one in my head, but let's just run through it so you see 16 times left parenthesis -1 raised to the 3 plus 18 times left parenthesis -1 in parenthesis raised to the 2. Hit enter, and out pops my answer of 37. So this one's equal to 37. Oops. And then I can do 1. If you do 1, you're actually going to wind up getting out 0. And then if you plug in, sorry, that was 1. I guess I should have gone in order here, huh? So let's go in order. If I plug in 0, I'm going to get out 0. If I plug in 1, I'm going to get out 5. And if you plug in 2 into your original function, you'll see you get out -8. And then I just look at these, and I look for the largest and the smallest. So let's take a look for the smallest first. So the smallest is a -8. So I'm supposed to circle this. So this is the smallest. So this is the my global min. And then the largest is a 37. So right here, I guess I only need to circle that. So let's fix. So this is the global max. So let's fix this one down here. You don't need to circle everything, really. And all I really need to circle is this piece right here. Right, this tells me everything. It tells me f of 2 is equal to -8, the global minimum. F of -1 equal to 37, the global maximum. Typically, by definition, the global min and global max are actually the heights. Same thing with the local min or local maxes. But you might as well give both pieces of information, and then you're never wrong. All right, let's do one more. Let's do part B. So let me copy this down. So on part B, what do we have? Let's change back to black again. So part B, I have g of x equal to ln of x divided by x, and this is on 1, 3. Let's make sure that's correct. Yeah. All right, so I'm going to do the same thing I did before. There's really no difference here. You do step 1. Again, you just copy it down. So find the critical points of g. So that's when g prime of x is equal to 0 or undefined. And so we're going to take this derivative, g prime of x. And now when you take the derivative, hopefully you realize it's a quotient rule because you're dividing two things. So you have a high and low. And so it's low d high. So I have x times derivative of the high, which is 1 over x, minus the high times derivative of the low, derivative of x is just 1, all over the low squared. And so this is going to be equal to 1 minus ln of x all divided by x squared. And now this is undefined. This is undefined when x squared is equal to 0. So that implies x is equal to 0. And I guess we should put and here. And x has to be greater than 0, right? Because of the ln x in the top. Remember, there's 3 things that cause a function to be undefined. 1, you can't divide by 0, so that's just x squared equal to 0 causes this function to be undefined. 2, if you have a square root, it has to be bigger than or equal to 0, and it's actually any even root, so square root, 4th root, 6th root. And then 3, if you have an ln function, it can only take in positive stuff. All right, so I know this has to be, x has to be bigger than 0, and it can't be equal to 0. All right, what's next? Oh, set it equal to 0. So that's the big one, right? So 1 minus ln of x all divided by x squared. Set it equal to 0. And you multiply both sides by x squared. And so this tells me, this implies that I get 1 minus ln of x equal to 0. And so then I know that I have 1 equal to ln of x. So I add ln of x both sides. And this is typically where students get stuck. And you get stuck because you forget what the ln says. So the log function says there's a little e here. E to this is equal to that x. So x is equal to e to the 1, which implies, right, x is equal to e. And then it makes sense. Oh yeah, if x is equal to e, ln of e to the anything is the anything. So ln of e to the 1 is the 1. So 1 minus 1 is 0. So that satisfies that equation. So you have these conditions, x is bigger than 0, or x not equal to 0, and x equal to e. And so I need to make my table. And so to make my table, let's write this down. So table. And let's go back to black. So let's put my table right in the middle here. So here's my table. I have x. I have g of x. And let's zoom out just a little bit more. And so on here, what do I have? Here's my original function way up here. And I start at 1, and I'm going to 3. So down here, let's start at 1 and end with 3. And there's only one number, e. So the idea is find g of 1, find g of e, find g of 3. And g of 1 is equal to ln of 1 divided by 1, which is equal to 0 over 1, so 0. And then this one is ln of e divided by e, which equals 1 over e. And then g of 3, that would be ln of 3 divided by 3. So now remember, I'm plugging into the original function right here to find these answers. And what do I get? Well, I'm going to have to use my calculator to check out. I mean, this is 0. So I know this is this one right here, I know is the global minimum. And I know this because these are all positive. Now I don't know which is bigger, 1 over e or ln of 3 over 3, so I'll use my calculator to determine this. So 1 over e, so 1 over second, e to the 1, not 11, 1. And I get out 0.3678, and then I plug in ln of 3, in parentheses, divided by 3, and I get out almost the same thing, but this one is a little bit bigger. All right, so if you look on here, if you look on here, 1 over e is just a slight bigger than ln of 3 over 3. So this is my global max. Oops, I ran out of the page there. So that's my global max. All right, we can make that better, I guess. All right, to check your answers, because you can always check your answer on here, what can you do? Well, I can just graph this function. So let's just run through this to make sure you understand that you can use your calculator to basically check all of these if you have time. So I want to graph ln of x in parentheses all divided by x, and I'm going to do it from 1 to 3 because it says you only care about things from 1 to 3. I'll zoom fit it, and if you zoom fit this, hopefully you see that you have a global minimum at 0 and a global maximum at e. Now it's hard to see because those numbers were so close. So you know what? I think I might go out a bit. So I might go to 5 and resume fit it just to see what's going on there on the right hand side because it's hard to see. It's going down. Okay, so this is good. So you can trace and plug in 0, and you see you get to go to. Now what happened here? I made a mistake, right? Because I plugged in 0. It doesn't begin at 0. It begins at what? At 1. So hit 1, and you'll see you get out 0. So that's good. And so that corresponds to what we have right down here. So if I plug in 1, I have my global minimum. And then my global maximum occurs up here. So hopefully if you plug in e, so second e to the 1, you'll get out, this 0.367. Your calculator actually has, if you hit second trace, it has minimum and maximums. So you can actually do this if just to check your work, like if you're really unsure, like I would do, left bound, right bound. And so you can just go to the left. When you think you're to the left of the maximum, you hit enter. Go to the right, you can hit enter. So I'm definitely to the right of the maximum. Give it a guess, just hit enter. And it'll point to the actual maximum. So that's E right there, and that's at 0.367, blah, 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 1 over E. Okay, I'm going to end the lecture here, and I'll see you guys tomorrow to do the homework in class.